Hi everyone, today I'm going to present you a singular-free inverse dynamics for underactuated systems with a rotating mass. So we begin with the underactuated systems literature review and related inertial coupling problem. And we will propose our combined wave kinematics to avoid the singularities due to inertial coupling. After obtaining the nonlinear dynamics and finding the inverse dynamics, we will show singularities in classic models with circular trajectories, and then we go through and find the singular-free model and verify it in simulation space. Generally, underactuated systems can be looked as follows, where the red terms are presenting constraint equations with no control inputs. This can be imagined as a passive carrier in the spherical rolling robots, or a passive link in pendulum or manipulators, where there is no control input. Please note that in 2 degrees of freedom, the inertia matrix are similar for all these considered models. In background, earlier studies begin by showing that the inverse of inertial matrix hits singularities and the differential equation integration breaks. A sponge proposed a strong inertial coupling condition for underactuated systems by using the positive definiteness of the inertial matrix. This was showing a singular-free model, but there was a geometrical limitations. Also, there was a coupling index to determine the actuability for different geometries. And the rest of the control strategies were based on these 2 conditions. So as a problem, we are trying to see how we can solve these geometric and angular limitations when we won't use inverse dynamics. So this inertial coupling is much more troublemaking in rolling systems as well, because we want to have a full angular rotations in these systems. So we study our modeling solution on rolling systems, where it is applicable for different 2 degrees of manipulators because of the similar inertial matrix. To avoid the singularities in inverse dynamics, we propose a small amplitude wave on the circular rotation of the mass, where the wave has the amplitude A and frequency of n and the phase shift of the zeta. In a classic rotating mass, the trajectory can transform to following form, and also the deviation of this combined wave kinematic is A sine. As the maximum value, this becomes the amplitude of the wave, and for the applicability of this combined wave, we assume that A is smaller than the core distance from the center of the sphere and also the sphere's radius. So we can ignore the effects of it in the dynamic and kinematic level. So please note that A can be even large, and we can realize it by different mechanisms like prismatic joints to move it in wavy forms, or a pipe in a wave form under fluid actuated systems. The kinematics of rolling carrier and on planar motion can be looked as follows, and by applying Lagrangian equations with arbitrary inertia for a pendulum lead or water in the pipe, we can apply the Lagrangian equations and then obtain the terms that are combined with our proposed wave. So to obtain the inverse dynamics, we find the output as a torque, and we specify our rolling carrier states. Therefore, we substitute our constraint equation to the main rolling equation with the torque, and we obtain our inverse dynamics. Please note that the new inertial matrix is transformed to different form right now. And by knowing that, we have to satisfy the positive definiteness for this matrix. But we have a new condition, which is comes from the M12 term. And because we know this following term is positive, we will hit the singularities if M12 is negative. Therefore, we propose a proposition where we will have a singular-free model if following properties satisfied, which is based on the M12 equation. And this can be obtained by for classic systems where A and N zeta are equal to 0. After obtaining the coupling condition, we check the singularity regions for different classic systems with the circular trajectories, where in the mass point system, the condition is transformed to following form, and we can see by using this inequality that the singularity region is getting larger as the core moves near to the center of the sphere. This also is much more critical when we apply strong initial coupling, and we see that for having a singular free model, the core must stay outside the sphere. This basically disobeys the physical mechanics, and also it's hard to limit the angular rotation in rolling systems, and the singular region will rotate as the sphere moves or rolls. In the second example, we add our arbitrary inertia to the whole system, where this can be the lead of the pendulum or the liquid in the fluid actuated system. We see that there is still a geometric limitation despite the included shift by the inertia tensor. So as a solution, we propose three main conditions, which is developed by M12 term condition, and we design our variables of a small amplitude wave with the following conditions, where delta mu's are just the constant values. The main idea of these conditions are obtained with finding the largest possible values on the right-hand side from the position, and then apply a Fourier transform to simplify the combined waves. And next, we find derivatives of each of these waves to find the minimum shift required, where in the figures you can see the yellow curve is showing the left-hand side equation, where we have always larger waveform which avoids the singularities, and we don't have a negative or 0 in M12 term. In a case study, first we consider the worst case scenario where there is no inertia tensor and we are in a singular region. We use following physical parameters, and our feed-forward control is a beta function where our desired state of the sphere is pi over 2. And by applying our combined wave kinematics, we will have a successful motion of the sphere, and we will not hit any singularity where the simulation shows. Now you can see our values that we have found from our conditions, which is considerably small, smaller than the sphere radius and the core distance from the center, and we have the output torqued successfully, and the sphere moves in a desired locomotion. It is important to note that A can be much more smaller when we have inertia in the whole system. And in the second case, we compare our modified model with classic rotating system, where we include arbitrary inertia and make it a pendulum system. And we see that the combined wave actually doesn't have a serious effects on the angular locomotion and the velocity of the whole system. In conclusion, we propose a small amplitude wave on the mass point, and then we applied it to nonlinear dynamics by using Lagrangian equations. We find the singularity regions in the classical rolling systems, and then we avoid the singularities in different examples by using our proposed conditions, and we verify it in simulation space. As the advantages, we can see our method is free from a complex algorithm and space transformation, which resolves the limitation of mechanism design due to the inertial coupling in underactuated systems with 2 degrees of freedom. It facilitates application in different controllers without angular limitations or configuration. And we plan to extend this theory to holonomic mechanism with multiple degree of freedom, and also design and find a way to design these various phase-shifted waves in the passive constraints to prevent the integrated singular configuration. I am thankful for your listening.